Number 7. The material with exceptional resistance to heat and cold. Imagine the lightest durable solid ever made. It looks like a ghost trapped inside a cube. Pale, translucent, and almost invisible. That's aerogel, a material that is 99.8% air held together by a delicate silica skeleton nanometers thin. It was invented in 1931 by Samuel Kistler, and for decades nobody knew what to do with it. You can hold a blowtorch under one side of an inch-thick aerogel tile and place your hand on top without burning. It's because aerogel defies what physics said was theoretically impossible, a material that neutralizes all three methods of heat transfer simultaneously: conduction, convection, and radiation. That's why NASA uses aerogel to insulate every single Mars rover and every single spacecraft. It melts at 1200 degrees Celsius and has 39 times more insulating power than the best fiberglass. It's the type of material you'll find inside the Iron Man suit. Number 6. The metal with a memory. Take a copper wire or a soda can and bend it, and you've permanently reshaped their atomic structure. But nitinol is an exception. It was developed in the 1960s at the Naval Ordnance Laboratory. You can twist a nitinol wire into a messy knot, drop it in warm water, and it springs back into a straight line instantly. That snap happens because the atoms switch crystal geometry without breaking their internal bonds. Cold nitinol rests in a soft phase called martensite, where atomic layers slide around smoothly whenever you push on them. Add heat, and those same atoms lock into a rigid cubic arrangement called austenite. That transition exerts enough force to lift heavy loads or hold open human tissue. Surgeons rely on this behavior to feed folded wire mesh stents through narrow catheters, knowing body heat will trigger the metal to expand once it hits the artery. A metal that remembers what it's supposed to be is one of the stranger things in physics. Number 5. The liquid that grows spikes. Ferrofluid looks like a dark, glossy pool of engine oil. Then you slide a magnet underneath it and the surface grows spikes. Perfectly geometric spikes that follow the magnet wherever you move it and collapse back to a flat mirror the second the field disappears. The reason it breaks physics expectations is that liquids are not supposed to hold structure at all, since surface tension and gravity constantly fight to keep any liquid surface flat. Under a magnetic field, the iron nanoparticles get pulled upward while surface tension resists, and the compromise they reach is those geometric spikes, a phenomenon scientists call the Rosenzweig instability. Ferrofluid was actually invented by NASA in 1963 as a way to pump rocket propellant in zero gravity, because standard pumps don't work when liquid floats freely in space. Since then, it has migrated into the ferrofluid seals inside every hard drive that protect spinning disks from dust, into the voice coils of high-end audio speakers where it acts as liquid cooling, and into experimental cancer treatments where nanoparticles are guided to a tumor and then heated by an alternating magnetic field to destroy cancer cells from within. Visually alien-like, practically useful and essential. Number 4, graphene. Graphene is a single layer of carbon atoms arranged in a honeycomb pattern exactly one atom thick. If you stacked 3 million sheets of it, the pile would be as thick as a pencil mark. Researchers at Columbia University measured its tensile strength at 130 gigapascals, roughly 200 times stronger than structural steel. And they calculated that puncturing a graphene sheet the size of plastic wrap would take a force equivalent to an elephant balancing on the tip of a pencil. This is from something you can't see with the naked eye and can apparently make with a piece of graphite and some Scotch tape, which was discovered in 2004 by Andrei Geim and Konstantin Novoselov, which ultimately led to being awarded the Nobel Prize in 2010. What makes graphene as a physics-defying material is that it doesn't just have one impossible property, it has several simultaneously. It conducts electrons over 100 times faster than silicon, which is why graphene transistors have been clocked at speeds that make current chips look sluggish. It conducts heat better than any known material, so graphene films are being tested as cooling layers in phone processors where heat is the main performance bottleneck. It's so atomically tight that helium atoms can't pass through it, making graphene membranes the most efficient filtration barrier ever measured, with desalination trials requiring a fraction of the pressure of conventional systems. Strength and thinness are supposed to trade off. Graphene can simply be described as alien material. It's extremely strong, lightweight, flexible, and astronomically effective. Number 3, metamaterials. Every material in nature bends light the same way. When light crosses from air into water or glass, it slows down and deflects at a predictable angle. Scientists call it the positive refractive index. And for decades, the assumption in physics was that a negative one, where light bends backward, simply wasn't something nature permitted. No natural material had ever shown it. In 2008, UC Berkeley engineers built microscopic silver wire grids smaller than the wavelength of light, creating artificial structures that force incoming light waves to bend backward, effectively creating a negative refractive index. They called it metamaterial. And when light enters a material with negative refraction, it curves in the opposite direction from what physics expects, which means wrapping an object in layers of this material causes light to flow around it the way a river flows around a rock. Nothing reflects back. And to any observer, the object isn't there. Functional cloaking for microwave frequencies has already been demonstrated in working lab devices, proving that seeing something isn't guaranteed just because it's standing right in front of you. Number 2, the metal that melts in your hand. Gallium is a real metal that conducts electricity and reflects light. Hold a piece in your palm, and your body heat causes it to slowly liquefy into a shiny puddle. Unlike mercury, which behaves similarly and is notoriously toxic, gallium alloys are safe to handle directly. A solid that turns into a conductive liquid in your hand without harming you is already an unusual thing, but the interesting part is what it can do as a liquid. Mixing gallium with indium creates a fluid alloy that stays fully conductive even in extreme heats of up to 2000 degrees Celsius, which makes this a versatile material. Engineers are using this fluid conductiveness to build flexible health monitors that stretch with your muscles and adaptive antennas that change their broadcasting frequency on the fly without needing a single mechanical motor. What came to mind as I was researching this was Terminator 2 and the villain that was played by Robert Patrick and the liquid metal. Who would have thought that liquid metal material actually exists? It's time to read more sci-fi books. Number 1, self-healing materials. Your skin heals, muscle repairs itself, you get sick and your body naturally fights off the virus after a week of rest. Biology has been running autonomous repair systems for hundreds of millions of years, but no human-made material have any self-repairing mechanisms. Crack a bridge beam and it'll remain cracked until someone finds it, assess the damage, purchase the necessary materials, then finally fix it. The idea of self-healing materials is practically impossible. Can you imagine buying a chair and after a week of usage, one of the legs breaks and it somehow repairs itself? It's hard to even think about. But self-healing materials change that by embedding repair chemistry directly into the material at manufacture. So damage triggers the fix automatically. The most common implementation uses microcapsules, tiny spheres of liquid repair agent throughout a polymer or concrete matrix. A crack breaks the capsules it hits. The self-repairing agent floods in, contacts a built-in catalyst, hardens and seals. The repaired zone isn't quite as strong as the original material, but it's close. And more importantly, you wouldn't have to discover it when it is completely destroyed and irreparable. Thanks for watching. Like and subscribe to see more.